one of the most common constructs in quantum algorithms, or is state preparation. It's the task of loading some specific probability mass function into the circuit, or just preparing its states. And what we see here is the way we declare it. So I'm asking to have a state preparation with a probability mass function, which is composed of 8 bars, 8 entries. And let's generate it. All right, and I've got a circuit here. And let's verify it does work in the quantum experience. Deleting the last barrier and measurements and fixing some bug which does not allow underscores. And as you may see, there is a permutation on that operator. It applies that gate in reverse order. So just to make it easy to follow, I will reorganize it. Just keep in mind that both solutions are valid because the user did not specify specifically that this first qubit should be the first qubit here. And if we take a look at the measurement probabilities, we see that indeed it's 5% and 11 and 13 and 23, just like in the input, where I requested 5 and then 11 and 13 and so on and so forth. However, note that the last 2 entries here are 4.5, 4.5, while I requested a different values. So what's important to note here is that this algorithm is approximated, and the user claims he is okay. He may bear an error of KL distance of up to 0.01, and she's willing to invest the amount of resources she's willing to invest in that part of the computation is bounded by 87 cycles. And now this looks like just 1 cycle, but if I open it, indeed we can see that it is first, it is deep, it is within the bound within the bounded range of depth, and it's also worth noting that it's not an easy task to compose such circuit from scratch. Once again, I can show the analyzer of such a file, and what we can see here is that the resulting QASM has, if we transpile it to native circuits, it has 78 cycles, while I've requested 87. So it's within the bound with U3 and CX gates considered as native gates.